Can you really find angles with inner products? In this video, we'll uncover the magic of inner products. We'll break down how these mathematical tools allow us to find angles between seemingly unrelated complex vectors. So in problem 8.6, find the angle in the sense of equation 8.28 between the vectors alpha as some complex vector, which we've seen before in previous videos, 1 plus I in the I hat direction, 1 in the j hat, and I in the k hat, and the vector beta, which is 4 minus I in the I hat direction, 0 in the j hat, and 2 minus 2I in the k hat. So these are both three-dimensional vectors living in the x, y, and z directions respectively. So we know that we have to do some careful manipulation with these with respect to equation 8.28. Now, this cosine is equal to the square root of a couple different orientations of inner products. Alpha with beta, beta with alpha, alpha alpha, beta beta. But what in the world do inner products and the angle cosine have together? Well, this is just the dot product. And we've seen this at the most basic of math levels and physics levels whenever we start dealing in calculus and vectors and the like. And so let's remember here that the dot product is asking us a couple different geometric questions. One of which that we're most curious about is what is the overlap of one vector, say A, onto another vector B? And as we see here, this overlap is guided by the dot product once we normalize everything with the magnitudes here. And then we see that this shadow that casts down on it, which there's a couple good write-ups which I'll link below. There's a Stack Exchange one that used ray diagrams to help showcase this. But nonetheless, we know that this overlap will change as theta changes. So if theta gets greater, closer to like 90 degrees, we see that this projection, the shadow, gets really small. Meanwhile, if I go to 0, that means that I'm laying on top of the other vector, which means I have a full overlap. Okay, so those are your two extremes. Now, a little bit more about the dot product as a refresher, which I found from Maths at Home, again link below, is given by this nice diagram slide write-up, okay? So again, knowing that the dot product is asking what is the overlap, we know that A dot B is equal to magnitude A, magnitude B times cosine theta. So rearranging this and dividing by the magnitudes, this is how we isolate the cosine, and this is the bases or the base formula for what is being built on in 8.28. Okay, so again, we see we have vector AB with some theta here, and if we have some vectors, in this case, these are two-dimensional, taking the dot product is just taking the components and multiplying them to themselves, which is what we've seen with the transpose conjugate method, doing row vector times column vector. All it does is multiply the components together. And then meanwhile, we see that these magnitudes are the square root with each component squared, which look like just the dot product of the vector in itself, i.e. alpha times alpha, i.e. alpha alpha in the inner product. So you may have recalled that from equation 8.28 that we had a square root over all of it. Well, this A dot B here can be squared in the magnitude and put inside the square root. And as we see, if we square that to put it inside the square root, that turns into alpha beta, beta alpha, because the magnitude squared is just the inner product times its complex conjugate. And that's how we end up with this. So, nice little refresher for that, but overall, this question isn't that challenging. We just have to take care of the math. So let's get started with these inner products. So start by reframing the vectors as column vectors. As such, we see that alpha and beta, just like we saw in that previous slide, by putting the I hat, j hat, k hats in this column vector notation, we see that they're pretty simple. And then if we want to find the inner products, once again, we see that we can go ahead and just take the transpose conjugate method. Transpose, take the conjugate, we get a row vector, row to column. We see that the components, x component, y component, z to z, and we get the same thing that we had seen previously. So that's pretty nice. As a result, once we distribute this side 1 to 1, 1 to I, that gives us positive I here. That cancels because we have negative I times 1. Those two cancel, and then we have negative I times I. which gives us negative I squared. 1 and 1 give us this positive 1, color change. And then negative I and I give us negative I squared. So upon simplifying, we have two constants, two complex numbers, or two imaginary numbers, which are going to turn to real, because we know I squared is equal to negative 1. So our negative and negatives cancel, and we're left with 2 plus 2 gives us 4. Not too bad. Now that we've seen how this math works out for this one, we'll kind of shortcut it for what's coming next, because I think the algebra is easy, all things considered, compared to the actual goal of this. So our next inner product then was beta with beta. So transpose conjugate with the dagger, move it, as you see highlighting the sign change on the complex parts, take their dot product. We have x component, y, z, easy enough. And as a result, when we distribute to simplify, we get 20 minus 5i after the zeros make that nice. But after we distribute both of these, we're good to go. As a result, this negative and I squared will end up canceling because I squared is negative 1. Easy enough. 20 plus 5 gives us 25. Love it. Then from there, we see that we need the inner product of alpha with beta. So transpose conjugate on the alpha vector gives us this row vector, which we multiply in. As a result, we see a similar calculation. Zeros, we love them for this reason. And then we get 1 minus 7i. Now, remember that we could switch the order of these two things by switching the conjugate. So we know that beta alpha is just equal to the conjugate of alpha beta. So since we already have this result, just take the conjugate of it and we're good to go. So that gives us 1 plus 7i. And then from here, we can use 8.28 and solve this equation out pretty well. So using the equation given to us, we're pretty good. We have the inner product, which we found using complex conjugates of one another, and then the inner product with itself, so just the dot product of itself. So magnitude here gives us 4, magnitude here gives us 25, as you recall. 1 minus 7i and then 1 plus 7i. All we have to do is take care of the algebra. Distribute this 1 to 1, 1 to positive 7. Negative 7i to 1, negative 7i to 7i. That's how we get negative 49i squared. But the cross terms here cancel. Love it. Then we see that we get a negative here, and then I squared goes to negative 1. So our negative and negative cancel, leaving us with 1 plus 49, or 50 over 100. Really not too bad, thankfully. That being said, both of these have a factor of 50 in them, so cancel them out, leaving you with root 1 over 2. Which leaves you, once you, instead of rationalizing it, which leaves you with 1 over root 2, which of course, if we're solving for theta, all we have to do is take the arc cosine of this, which we know that the arc cosine for two, assuming positively oriented vectors in the domain of the arc's cosine will give us 45 degrees, or for the math purist, pi over 4 radians. Not too bad at all. So pretty fun video, very, very nuanced and needed. Again, dot products, cross products, they take this kind of new kind of formalism with inner products, outer products, things like that. Very much needed. As a result, if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.